Greetings, science appreciators! Today, let's explore something truly electrifying: flexible batteries. Think about the devices we use every day. Your phone is a rigid rectangle. Your laptop is a stiff clamshell. But what if they didn't have to be? What if your electronics could bend, fold, and stretch just like a piece of paper or fabric? This is where flexible batteries come in. They are the power sources designed to move with our technology, opening up a world of possibilities for gadgets we can wear, fold, or even implant. Imagine a world powered by things that aren't just flat and hard. These aren't just your everyday, run-of-the-mill batteries. Traditional batteries, like the one in your TV remote, have a very strict, solid structure. If you tried to bend one, it would likely break and leak, which is not safe at all. Flexible batteries, however, are built differently. They use materials that can be twisted, compressed, and stretched without losing their ability to store and deliver energy. This is incredibly important for the next generation of electronics. We're talking about smart clothing that monitors your health, electronic newspapers that can be rolled up, or medical patches that deliver medicine while conforming perfectly to your skin. So, why is this so revolutionary? Because form follows function. The shape of our devices has always been limited by the shape of their power source. By creating batteries that can adapt to any form, we unshackle our engineers and designers. They can create wearables that are truly comfortable, medical devices that are less invasive, and consumer electronics that are more portable and durable than ever before. This shift from rigid to flexible power is not just a small step. It's a giant leap for how we interact with technology. It's about making technology feel more natural and integrated into our lives. But before we can all start wearing our phones like wristbands, we have to be absolutely sure these batteries work, and work safely. How do we know a battery is flexible enough? How do we know it won't break after being bent 1,000 times? And how do we ensure it still holds enough power to be useful? This is where testing comes in. Scientists and engineers have developed a whole suite of tests to push these batteries to their limits, ensuring they are ready for the real world. It's a critical process that turns a cool idea into a reliable product. First up, let's talk about geometry. When we say a battery is flexible, what does that really mean? It's not just about being able to bend it once. Scientists need to measure exactly how it bends, how much it can bend, and how many times it can bend without failing. One of the most common tests is the bending test. Imagine taking a small, thin battery and wrapping it around a pipe or a cylinder. Scientists will use cylinders of different sizes to find the smallest radius the battery can be bent around without getting damaged. This measurement is called the bending radius, and it's a key indicator of flexibility. Think of it like this. A flexible ruler can be bent into a gentle curve, but if you try to fold it in half, it will snap. A flexible battery has similar limits. Testers might bend a battery back and forth thousands, or even hundreds of thousands, of times to simulate years of use. For a smartwatch band, this might mean mimicking the motion of putting it on and taking it off every single day. They carefully check if the battery's performance changes after all that movement. Does it still hold a full charge? Does it deliver power consistently? The goal is a battery that works just as well on its 10,000th bend as it did on its first. Another important geometric test involves twisting and stretching. Some applications, like smart clothing, require batteries that can handle more complex movements than just simple bending. For these, testers will use machines that twist the battery along its length or stretch it like a rubber band. They measure how much the battery can be deformed before its internal layers start to come apart or its electrical connection is lost. The results help designers understand what kinds of devices the battery is suitable for. A battery that excels at stretching might be perfect for a fitness shirt that moves with an athlete's body. The shape of the battery itself also matters a great deal. Is it a long, thin strip, a small, square patch, or something else entirely? The form factor is often designed with a specific use in mind. For example, a battery for a medical implant might need to be shaped to fit around an organ without causing discomfort. Testers evaluate how well the battery maintains its intended shape and function under stress. Ultimately, these geometric tests are all about defining the physical limits of the battery, ensuring it can handle the twists and turns of everyday life without breaking a sweat or its circuits. Next, we move from shape to strength. This is where we get into mechanical testing. It's not enough for a battery to be flexible. It also has to be tough. Think about a phone in your back pocket. It gets sat on, squished, and bumped around. A flexible battery in a similar situation needs to withstand that pressure without breaking. Scientists use specialized machines to test this. One common test is a compression test, where a machine applies a steady, controlled pressure to the battery, simulating the force of being squashed. They measure how much force it can take before it deforms permanently, or, worse, fails. Another key mechanical property is tensile strength, how much the battery can be pulled before it breaks. This is especially important for batteries that might be woven into fabrics or used in stretchable electronics. A machine will clamp onto both ends of the battery and pull it apart, carefully measuring the force required to stretch it and the point at which it finally snaps. This tells engineers how durable the material is. A good flexible battery needs a balance. It must be soft enough to bend easily, but strong enough to resist tearing when pulled. But what happens when a battery is bent too far, or too many times? This is a question of fatigue. Materials can get weaker over time with repeated stress, even if that stress isn't enough to break them right away. Think about bending a paperclip back and forth. Eventually, it will snap. Scientists perform fatigue tests on batteries, repeatedly bending, twisting, or stretching them on a cycle to see how they hold up. They look for tiny cracks, delamination, where the layers of the battery start to peel apart, or any other signs of wear and tear that could lead to failure down the road. All of this mechanical testing is crucial for safety and longevity. A battery that breaks can be a serious hazard, potentially leaking harmful chemicals or even causing a fire. By pushing these batteries to their mechanical limits in a controlled lab environment, we can ensure they won't fail unexpectedly when they are in your clothes, on your skin, or in your foldable phone. These tests help us build batteries that are not only flexible, but also resilient, robust, and ready for whatever we throw at them, or however we bend them. Finally, we need to talk about what makes a battery, its energy. A battery can be the most flexible, strongest, and toughest in the world. But if it can't hold enough power to run your device for a reasonable amount of time, it's not very useful. This is where we measure energy density. Energy density tells us how much power a battery can store in a given amount of space, or for a certain weight. It's the reason your tiny smartwatch can last all day, or why your phone can play videos for hours. High energy density is the holy grail of battery technology. There are two main ways to think about energy density. The first is gravimetric energy density, which is the amount of energy stored per unit of weight, often measured in watt-hours per kilogram. This is super important for wearables like smartwatches or fitness trackers, because you don't want a heavy, clunky battery weighing down your wrist. The second is volumetric energy density, which is the amount of energy stored per unit of volume, watt-hours per liter. This is critical for devices where space is at a premium, like a foldable smartphone or a compact medical sensor. Testing for energy density involves charging the battery to its maximum capacity and then discharging it under controlled conditions. Scientists measure exactly how much energy it delivers from full to empty. The real trick with flexible batteries is to perform this test while the battery is being bent, stretched, or compressed. Does the energy capacity drop when it's wrapped around your finger? Does it lose its charge faster after being folded 1,000 times? A great flexible battery will maintain a high energy density no matter what shape it's in. And that brings us to the future. To make even better batteries, scientists are now using advanced computer models and machine learning. Instead of just physically testing every possible scenario, they can simulate how a battery will behave under different kinds of stress. These smart computer programs can predict battery health, estimate its lifespan, and help researchers design new materials that are both more flexible and more powerful. By combining rigorous physical testing with intelligent computer modeling, we are accelerating the pace of innovation. This meticulous work ensures that the next generation of flexible, wearable, and foldable devices will be safer, longer lasting, and more reliable than ever before. Consider that,